This series focuses on data structures and algorithms content, and in this recording in particular I will talk the third part, part 3 of the selection sort algorithms of series, complexity analysis, particularly big O analysis. We can see the complexity of an algorithm from the perspective of the amount of time required and amount of memory space required, called as time complexity and space complexity respectively. Talking about space complexity for a selection sort algorithm, this is the code for this selection sort algorithm where the code is placed inside a function. From this function we can see that the algorithm merely requires local memory space, which is actually the extra memory space required by the algorithm um, or the function to perform the sorting tasks. Memory space required for variable temp, and that required for iteration indices I and j, and some temporary memory space may be required to evaluate the expression like this and or like this. Therefore, the space complexity of the selection sort algorithm is big O1. It is a constant space complexity. Now let us take a look at time complexity from the top level or a course level perspective. The course level analysis is not concerned with the detailed and precise counts of the operation involved. For example, counting the statements, individual statements in the swapping operation, or counting individual statements. It is more concerned about the rate at which what computation actually dominates the total computation. Here the external loop or outer loop controls or executes in sequence this is the entire logic of each pass of the algorithm. For each pass, for example, in the first pass, this entire logic gets executed with I equals to 0. In the second pass, it gets executed with I equals to 1. In the third pass, it gets executed with I equals to 3. In the last pass, it gets executed with I equals to size minus 2. So in each pass, the algorithm picks the index value as a index of a minimum element of the array. That means it actually records the value of I as a index of the minimum value, which means that it assumes that in the first pass it assumes that the first element is a minimum element. In the second pass it assumes that the second element is the minimum element, and the inner loop in this inner loop, the purpose of this inner loop is this loop is to actually update that presumed or assumed minimum index value. So if there is another minimum value in the array which is smaller than the selected minimum value, then it will update that minimum index with that index of that element. Now after that we have a swapping operation. This swapping operation, if we assume that this swapping operation takes place only for size minus 1 times, then then the external loop will actually execute for size minus 1 times. Therefore it will execute for the same number of times. For example, just to clarify, if we assume, sometimes in some iteration this swapping may not be executed, sometimes it may be executed, but in the worst case we can assume that swapping is executed or it is run for all the external iterations. That means the complexity contributed by this swapping operation for the entire execution of the algorithm will be only size minus 1 complexity. So we actually are focused more on this inner loop, how many times this inner loop is actually executed. So this inner loop is executed for, in each pass it is executed for size minus I minus 1 times, which means that in the first pass, in pass 1, it is executed with the if statement inside this for loop is executed for, let's say, pass size minus 1 times, because in the first pass I equals to 0, so it is size minus 1. In the second pass it will be with I equals 1, it is executed for size minus 1 time, size minus 2 times. In the third pass it is executed for size minus 3 times, and in the for the last pass it will continue that way. In the last pass it will be executed by with for 1 times, only 1 times. So now if we calculate the total number computation in over all the passes, we need to add this values 1 plus 2 plus 3 plus size minus 3 plus size minus 2 plus size minus 1. So using the summation formula that I have used in the analysis of the bubble sort algorithm in previous recording, we can get this expression where we have assumed that the lowercase n is actually we have actually replaced this size by this lowercase n to make it the equation look more easier to explain. Now if you have this expression, actually this expression you can get if you add all these uh, I mean size values 1 2 3, and if we replace this size by 1, then it will be n minus 3 plus n minus 2 plus n minus 1, and there is a summation formula which is n times n plus 1 divided by 2. If we use that formula, we can get this complexity. Therefore, the complexity of the selection sort algorithm is big O n square, which is a quadratic complexity. Finally, the best case, average case, and worst case complexity, I mean big O complexity in the best case, in the average case, in the worst case, in all cases it is big O order, I mean n square. This is because the comparison or if statement inside inner loop actually is executed for uh, for for the execution of all the external and internal loop, and external loop and internal loop are actually executed for the all the comparisons made. So and if you have a external loop inner loop, then it is obviously is going to be n square complexity. So this is the end of my presentation or discussion here. Thank you for watching this video.